Prompted by the remarks of Max, who was here, he may be coming, and Kumar, who talked to me afterwards, I realized I hadn't made one point clear, and perhaps more to the point, I hadn't really understood it myself, and that is the argument that I gave last time would work, as Kumar pointed out, when the L function of the representation pi is analytic in any right half plane. And the problem with that's just simply not true. It doesn't work under those conditions. And the problem is that the argument that I made, rho was a representation of the L group, of the dual group, G hat to GL of V. And I had assumed that the trace of rho tilde was equal to the trace of rho. Conjugate. And that is not true. The reason is, what makes things like that true? And so I think this argument of Langlands is really quite subtle, and I don't know that it's ever been written up. Somebody should write it up in detail. It's just, as I say, it's just one page of Langlands' article. So I think it probably doesn't hurt to make a slight digression into general background. I mean, where would things like this come? They would come from general abstract harmonic analysis. So let's say abstract theory of non-abelian topological groups. And we assume that H, so just remind you, I think, well, anyway, this is easier for me because I was brought up on these things. I think I took a couple of graduate courses early on this business, popularized or largely done by Mackey, but others as well. And it turned out not to be quite the right way to look at things because it wasn't rich enough. But in any case, if H is a locally compact unimodular, we'll assume, topological group, there is, you can attach to H, and I guess it's a functor, to the, what would be the analog in this much sort of more general case of the group algebra. So the group algebra of G, and what is it? Its analog, it's L1 H. The L1 under convolution, the L1 functions on H. So this is a Banach star algebra. under convolution, of integrable functions. F on G on H. H is, we'll just use the letter H, not to get it mixed up with what we were talking about, the more specific situation we were talking about. So okay, so this is it's L1 functions with, of course, Haar measure. That's maybe not visible, but in any case, the L1 functions with Haar measure, left and right Haar measure, are the same for a unimodular group. And then there's a very simple lemma in this general situation. What we were asking for before is very closely related to this lemma, but it's not true in the setting that we had posed it before. And the assertion is that there exists a canonical bijection from oh, I forgot to say something. Sorry, I'm going to have to. Group algebra, it's a Banach star algebra, if you're familiar with those terms, and it doesn't matter if you're not. Under convolution, so it's an algebra under convolution with respect to the Haar measure of integrable functions, but star means it's a star is an involution. F star of x is equal to f of x to the minus 1 bar. So that was, we saw that in the thing that with rho up there, or something very close to that. But this is where it comes from. So then I'll just say this is a completely elementary lemma. There exists, well, it's I don't know about the bijectivity of it. I didn't really think about that, but I'm going to state it that way. There exists a canonical bijection from irreducible, and it's critical that they be unitary, irreducible unitary representations I on this group to irreducible star representations pi, I guess I could write it as pi star of L1 of H on the group algebra. So this would be something that people would study in the first course in representations of finite groups, how you can talk about a representation of a finite group, and how equally you could think of the representation as a representation of its group algebra. And L1 of H really is, if you think about it, it really is the analog. If you take into consideration the topology and the norm, the integral, it really is the analog of the group algebra. And so there's a canonical bijection from this to this. So in other words, that, what do I mean here? I mean that pi f star f star being this involution here, is equal to pi of f star. So f in L1 of h, and this is the adjoint operator on the pi acts on a Hilbert space. It's yes. I'm not sure that we can quite state it in those terms. We have to have it as a representation. No, the analog of unitary is a star representation. That's the analog of unitary. Oh, just anything in there. Star stands for just any variable. The character. Okay.
So pi of x is some Hilbert space.
That's right. That's right.
Would you say it's a representation of the algebra?
It means that pi of a convolution is the composition or the product on the Hilbert space.
From the B star algebra to the space of operating.
On the Hilbert space. That's right.
Respecting star.
Respecting this, that's the multiplicative property, and then this, also respecting the star.
So it's more than an algebra homomorphism, it's a B star map.
That's right. That's right. And the fact the analog of it being the fact of it being a B star map is what the unitary property that it inherits from the analogous representation on the group. So let's say the proof. I didn't try to see that it was bijective, but I think it must be elementary. It's certainly elementary in the case of finite groups. But pi of f1 star f2 is equal to, you have this property here, pi of f1 composed with pi of f2. And this is simply a change of variables. In the integral. Okay, so I didn't say what pi of f was. I don't think I stated that. Where but pi of f, given a representation pi of the group, then obviously pi of f is going to be the operator on the Hilbert space of that representation, got by taking the integral over h of f of x, pi of x, dx. And so that really is, if one looks at group algebras for finite groups, that's really what one is looking at, although it doesn't, sort of at first glance, it doesn't seem like that, but that is what it.
Definition of pi on the algebra and that other pi inside the integral solution.
That's right. That's right. So it's the same. It's the same well, it's the same representation. Pi and a Hilbert pi in a Hilbert space on a group gives you pi on a Hilbert space on the algebra, except unitary, except multiplicativity. Multiplicativity is under convolution, and a unitary means star, but it's star. And so just to see that second point, so this comes immediately from a change of variables in this integral. Perhaps I think perhaps you got to use the unimodularity of the Haar measure, and then but secondly, pi f star. Okay, so that's going to be the integral over h of f of x, pi of x dx. Okay, so what I want then is the adjoint operator of that. That's an operator on the Hilbert space. I want its adjoint. So an adjoint of a scalar multiple of an operator is the complex conjugate of that scalar multiple. So that would be f of x bar, and then pi of x here is the adjoint of the operator pi of x. So that would be the adjoint of the operator given by the integral. It's this times this. And so that's equal to, this is supposed to be unitary. So it's the integral over h of f of x bar, pi. So because this is unitary, this is equal to the inverse operator. In other words, pi of x to the minus 1 dx. And since pi is unitary, all right, so that's equal to the integral over h of f of x to the minus 1 bar pi of x dx. That's a property of unimodular groups. The Haar measure, because the Haar measure is left Haar measure is equal to the right Haar measure.
Inverse map preserves Haar measure.
That's right. That's right.
What you're using in the unimodular.
Yeah. So I'll just say since the integral of any function h of x dx equals the integral of h of x to the minus 1 dx if h is unimodular. All right. So this is equal then to, we've got, what's that? I have, yes, that's my star operator on f, pi of x dx. So in fact, that is pi of f star. So that is, that's what we're asking. Did I write it down? Yes, I wrote it down here. That's what we're asking of representations. That's what a star representation of the algebra would be. And it is the, as we see, it's the analog of being unitary. Okay, now the argument that we would be using for Ramnujan, so which I went through. So this is the argument that Langlands uses for Ramnujan. What were we looking at? We made, following Langlands, we made a simplification where we, in fact, we haven't even defined what Ramanujan would be. Well, I said tempered, but I haven't defined what tempered would be. So I haven't really said what Ramanujan would be in the case of a representation pi p of the local p-adic group, what tempered would be unless it's unramified. And unramified, for tempered, it means that it's induced from a one-dimensional unramified character on a Borel subgroup. So the argument of Ramnujan concerns, in the case that we're following, and by the way, the notion of it being tempered for representations that are not unramified, it's very similar to this, except it needs something else. It needs some more machinery. It needs, well, it really needs Langlands' local classification of representations, which we will talk about presently, not today, but soon. And then it fits right into this. So it really was very inspired. This is the case that it's perhaps most important. This case of Ramnujan, it concerns the classical case, for example, but it also is the one that's easiest to describe, even though it's pretty subtle. And it's easiest to describe in terms of the inducing representations. So I'll just say the argument for Ramnujan that we have been talking about it concerns the subset I'm going to write it as pi unitary GP did I say up here? Yes, GP KP. I think I left something out. Anyway, let me just finish this. Concerns the subset. So I'm going to be writing KP for GQP for simplicity, and I'm going to be writing KP for GZP, maximal compact subgroup. Of GP. So I'm going to be writing that. Okay, so then I'm going to therefore, so this is I'm going to write pi unitary GP KP. So this is a long sentence, and this is just an aside here, but I am going to be writing that for so this is the concerns the subset of unitary representations. So it's the subset of representations pi p that are induced from BP to GP, CP, induced from a unitary unramified character, and I mean an abelian character, CP I'll write this down first and then just remind ourselves what it would be, TP intersection KP, And so this is so I don't know that I really went through the definition of an induced representation from a Borel subgroup of a group, but it's a standard definition. So in any case, this concerns representations induced from a Borel subgroup attached to a character on TP. So this is to be extended. I'm just going to write this down. It's a rather ungainly sentence. Extended trivially from TP to BP, where T is contained in V, is contained in G. So I think before we talked about T hat contained in B hat, contained in G hat, the complex dual group. But now we've got this group G over Q. If we already fixed a T hat, B hat, and G hat. And if you fix one of those, it'll fix one of these for you for G. Parallel to the previously chosen T hat, B hat, G hat. All right, so the argument for Ramnujan pertains only to these representations. These are the unramified, they're not just unitary representations, and they're not just unitary representations, but they are unitary representations induced from this very particular kind of character, an unramified character, CP on TP. That is to say, it's trivial on the intersection of KP with this maximal compact subgroup. And over here, we've got unitary representations of H and star representations of L1 of H. What we've got here is something different, and that's why that adjoint condition up on top there doesn't work. We're only working with a very particular class of representations. And most importantly, they're representations which upon restriction, representations once you induce these up, they are representations of GP whose restriction to KP contains the trivial representation with multiplicity 1. I'm not proving these things, although they're not hard to prove from the definition of the induced representations, but an induced representation from a Borel subgroup, I guess maybe any irreducible representation contains, when upon restriction to K, it contains the trivial representation with multiplicity at most 1. So these are representations which actually do contain the trivial representation of K. And for that reason, what will play the role of the full convolution algebra on G when we're only taking these very particular representations? Pertains to these representations and with the convolution I'm only considering these representations which have a K invariant vector, then I'd be thinking about the convolution algebra, not all of L1 of GP. So the convolution subalgebra, L1 GP, KP, of Kp by invariant. So did I mention this before? By invariant functions in L1 of GP. It's a subalgebra because if you got an integrable function there, it's certainly going to be integrable on this, well, on this subalgebra. And so this thing, we won't really need to consider all of L1 here. So the convolution algebra of L1 functions, or rather, it's enough to consider the dense subalgebra. Of K bi-invariant functions of compact support, which are continuous. So the dense subalgebra, and this is what's called the Hecke algebra, HP, the continuous compactly supported functions, GP, KP of L1. GP, KP. And that is actually, it's simple enough to be something you can work with, but complicated enough to be interesting. It has interesting structure to it. But it is only when we do this, when we do this replacement, whoops, I'll leave that there. It is only then, when we confine ourselves in the appropriate way to this subset of irreducible unitary representations of GP and this algebra, this Hecke algebra, it is only then that we get the property the trace of rho with any argument there equals the trace of rho bar quoted above. This is for a representation where rho tilde of CP, let's say, CP just being a variable, equals rho T CP to the minus 1, that's the definition, is the contragradient of the finite dimensional representation rho of G hat. Now I told Max, and Kumar is not here, I told them that they both raised questions of this that really boiled down to this last Friday, and I unfortunately started thinking about them during the concert I went to, which complicated. I wasn't paying too much attention to the concert. I don't know whether I've completely gotten this straight, but this is the issue. It's simply not true that you can appeal to that if you're dealing with all representations. This is, after all, a different representation. This is a representation of the group G hat. It's not a representation of GP. And to see that you get something like this, I didn't think whether you could do it directly for this subalgebra of the Hecke algebra, this subalgebra of L1 of G, namely HP or C sub C of GP comma KP. But there's a basic property of this Hecke algebra, which I will quote presently and won't prove, but it's not hugely difficult. It concerns something called the Sataki transform, and it relates this algebra to something even simpler, something that is really directly tied to rho being a representation of G hat. It's a finite, and it's a very different kind of representation, of course. It's not an infinite dimensional unitary representation. It's a finite dimensional representation that would be classified by, say, Weil's theory of highest weights. All right, so maybe I'll just, this is the aside, but I will just add so how do the inducing characters I haven't really these CPs, remember CP is something that you get from when you start to look at a representation pi p, an unramified unitary representation pi p that is a component of a cuspidal automorphic representation of an cuspidal automorphic representation pi. So this is rather far removed from what we seem to be talking about there. I'm talking about it as an inducing parameter, CP, and so my question is, how do the inducing parameters CP, which I've alluded to there, and which I've taken to be parameters for induced unramified induced unramified representations of GP. So how do the inducing parameters relate? We still have to, even though we're not treating the full group algebra there, we're treating this subalgebra, this Hecke algebra, but we would still want to know how in order to get something like that above, how do the inducing parameters relate explicitly to the Hecke algebra? So I think I need to, so that's what's known as the Sataki transform, which I will state. I probably won't, I'll be finished with this at the beginning of the next hour, but I think it would also be good to just review or describe some properties that Langlands uses in his article and which are used everywhere in the theory of algebraic groups as they relate to representations. So this is another description of something related, but so this is a question. So before I state what the Sataki transform does, Let me just introduce a couple of other things. Following Langlands. So this is one of the things that actually makes Langlands' article a little bit difficult to read, and it's understandable. Excuse me. These things were barely invented when he wrote this article. Sataki transform, in fact, wasn't done. I think he just stated it as a lemma, saying that it would be done soon. He didn't even deign to call it a conjecture. He took it as a lemma that he no doubt could have proved, but I don't think that it was formally established, and it wasn't understood by people at the time. But in any case, there's related things that are in his article that we should understand. So this is basic stuff for algebraic tori. Let me set x equal to x star of t. What's t? T is a split torus in the group in the split group GP. GP I'm writing for this group of p-adic points in the group. So G is a split group. T is a maximal split torus sitting inside a Borel. And so one writes x star of t for, and so these are now this is to be regarded as an algebraic group, and it's Hom T GM. GM's also to be regarded as an algebraic group. It is another way of writing GL1, but I'm not talking about the group of points. I'm talking about these simply as algebraic groups. And yes. That's right. So it's tricky. What I'm thinking of here, I'm thinking of this set. These are by definition representations induced from an unramified unitary character on a Borel subgroup, on a maximal torus sitting inside a Borel subgroup. That's what these things are. This rules out, for example, for GL2, you have the principal series, the unitary principal series that are induced from a unitary character on a Borel subgroup. You also have some other ones. They arise in two different kinds of way, but there's something called the complementary series. Those are representations also induced from a character on maximal split torus in a Borel subgroup, but it's not a unitary character. Those are called the complementary series, and we don't count those. They're unitary, but they're not unitary directly as induced representations. You have to redefine the inner product on one of those representations to get something that's unitary. I mean, it's just a little bit confusing, but if you take the induced representation from a non-unitary character, say for SL2, take a non-unitary character on the group of diagonal matrices, but a non-unitary unramified character. In other words, you raise these things to not an imaginary power, complex power, but maybe an but something which also contains a real power. And if that real power maybe is less than 1, you can actually, that's what are called the complementary series, those induced representations. And they can be made unitary. They're equivalent. They're non-unitarily equivalent to a unitary representation by defining another inner product than the one that you're given by as an induced representation. And so I do not want to include those. They're not going to be, their L functions are not going to be analytic in the right half plane, real part of S bigger than 1. They're going to have a singularity. Better be a little bit careful. They're not going to be absolutely, they're certainly not going to be absolutely convergent. The L functions are certainly not going to be absolutely convergent on the hyperplane real part of S bigger than 1. It's going to be real part of S bigger than 1 plus U, where U is the little real parameter that you put into the inducing parameter. And so they're not going to be absolutely convergent. They'll have a singularity. And so those ones have to be ruled out. So I'm considering only these representations that are induced from a unitary parameter. Only those ones. All right. So I'd like to. So it's. I mean, this is standard business for representations of people that do algebraic groups. One writes X upper star T for a torus as the group of homomorphisms of algebraic groups from this algebraic group to this algebraic group, GL1. And this is isomorphic. It's a lattice, and it's isomorphic then to Z to Z plus Z several times. So that's a lattice. And what's, I shouldn't maybe not say it's too confusing, but you use additive notation in this lattice. Lambda 1 plus lambda 2 is then the element for lambda 1 and lambda 2 in L. And the sum of those two things, because I've written this lattice additively, is the homomorphism which evaluated at any t. This is just standard notation. It is multiplicative. So it's a homomorphism. So this mapping from this lattice to this abelian group is a homomorphism, but where the additive notation in the lattice gets transformed into the multiplicative notation there. And so then for any field, so one really does have to be able to work with these things all the time. Harish Chandra had his own notation for it. Burrell had other notation, and we won't go into that, but then for any field, F, TF, so T is a torus, then that's equal to Hom L F star. And this is now a homomorphism of groups, and this is but still isomorphic to F star cross F star, where T and something in here of lambda 1 plus lambda 2 is by definition, this is by definition, and this is by definition, is equal to T lambda 1, T lambda 2. So in both situations, additive notation gets transferred to multiplicative notation. This is, as I say, standard convention for dealing with algebraic tori. This is introduced in Langlands, the beginning of that article, but it's also everywhere in Langlands' later article, like a year or two later, algebra, what's it called? Representation, forget what it's called, but representations of tori. Of algebraic tori. And it's, I've never really gone through that. You just have to Google it. It came maybe a year later after he certainly had this done, I guess, when the Bachner article was written. But he published it about a year later. And what he does is he proves the conjectures. He proves functoriality in the case. I mean, his conjectures in the Bachner article are about reductive algebraic groups, product of a semi-simple group with an algebraic group. And it's an algebraic group being a reductive algebraic group, that is to say a torus, not the additive group. And so this is a special case of all of his conjectures, and he goes through the classification of local representations of a torus. He goes through the classification of global representations, that is to say representations of TA that occur in L2 of TA over TF. And in particular, he verifies functoriality. So it's a challenging paper, but a very simple paper if you're up in all of these techniques. But it's just I mean, Langlands describes it as an exercise in class field theory, and it really is hardcore class field theory, specifically group cohomology, applied to algebraic tori rather than to the multiplicative group of a field. That would be like GL1, which is what is used for hardcore algebraic, hardcore abelian class field theory. This is one step beyond that. This theory that went into it, group cohomology, not just for GM, but for algebraic tori, was discovered or introduced by Tate Nakayama following class field theory, maybe 10 years previous to that. And in any case, this notation occurs all the way through that paper of Langlands, and it's, as I say, it's a challenging paper. Langlands apologized for the paper and said, "Pardon me if my techniques my techniques seem simple. If I'm repeating things that experts know well, but please consider the fact that the author has never co-cycled before and has to get used to his vehicle," or something like that, some variant of that. So in any case, I'll just spend a couple of minutes next time reviewing what these things are, what the characters CP amount to. I mentioned it for GLN before. There's really two of these characters. There's the characters CP that come into the unramified, come into the unitarily induced representations. And then there are the parameters which I could call CP of pi, which are local components of cusp forms, and for which we do not know that they are, they're characters for induced representations as well, but we do not know yet that they are unitary, and that's what Langlands establishes, given the principle of functoriality. So we'll just review that very briefly next time. Then we'll get on. I mean, this is I shouldn't. Yes, they can. They include the co-roots. They include the co-roots. Yes, but it's a full lattice. It's like the lattice generated by the co-roots.
With a pinning, I suppose.
Pardon me, yes. Well, that's like the choice of the Borel subgroup gives that to you.